commutation techniques. Coming to this forced commutation. In natural commutation, the SCR is going to turn off depends upon the nature of the supply. During the positive half cycle of the supply, the anode is made positive and cathode is negative. Corresponding that the SCR is in forward biasing mode. If you provide the gate signal, then the SCR comes to the on state. Once the current flow through the SCR crossovers the latching current, after that you remove the gate pulse, continuously the SCR will be in the forward conduction state. At omega t is equal to pi, output voltage is 0 and output current is 0. After that, from pi to 2 pi, during the negative half cycle of the supply, the anode is negative and cathode is positive, the SCR is automatically goes to the off state. That is natural commutation or line commutation or class F commutation. Coming to this forced commutation, if you go through this DC supply, whenever the SCR is energized by the DC source, here this is the anode, cathode and the gate, it is the positive terminal and it is the negative terminal. When anode is made positive with respect to the cathode, then the SCR is in forward biasing mode. If you provide the gate signal, SCR comes to the on state. Once the current flow through the SCR crossovers the latching current, then this gate loses its control on the conduction of the SCR. So SCR is continuously in the on state. So how you turn off that SCR? So the current flow through that SCR can be made forcibly to the 0 by using some external circuit. Then the current flow through that SCR is either equal to the 0 or below the holding current by using some external circuit. That phenomena is simply called forced commutation. In forced commutation, we forcibly commutate. Commutate is nothing but turn off mechanism of the SCR. We forcibly reduce the current flow through the SCR below the holding current or 0. That phenomena is called forced commutation. The external circuit which is used to turn off that SCR is called commutating circuit, and the elements which are used in commutating circuit are called commutating elements. Mainly the commutating elements are inductor and the capacitor. And depends upon the configuration of these commutating elements or arrangement of this commutation circuit, the forced commutation techniques are mainly classified into 5 types. Those are class A commutation or self or load commutation. Second one, class B commutation or resonant pulse commutation. Third one, class C commutation or complementary commutation. Fourth one, class D or auxiliary commutation. Fifth one, class E or external pulse commutation. These 5 commutation techniques are used whenever the circuits are energized by the DC source, like in chopper circuits or inverters. If you go through the choppers, DC to DC converters, here the input is DC. Whenever that SCRs are energized by the DC source, you need to use this forced commutation technique. Another application of this forced commutation, inverters. Inverter means which converts DC to AC. Here also that inverters are energized by the DC source, so you need to use forced commutation. So coming to this, first one, class A or self or load commutation. So here, this is the circuit representation of class A commutation. In this, source, SCR and the load is the main circuit. Source, SCR and the resistive load. Here the commutating elements are inductor and the capacitor. Here the commutating elements are inductor and the capacitor. If you go through the class A commutation or self commutation or load commutation, the commutating elements which are inductor and the capacitor always connected in series to the SCR. The SCR which is going to be commutated, For that commutating SCR, the commutating elements, inductor and the capacitors are always connected in series like this. Here this is the main SCR, I just want to commutate. For that, the commutating elements L and C are connected in series. Similarly here also, this is the SCR, I am going to be commutated, and the commutating elements L and C are connected in series. Depends on the value of load resistance, that load resistance may be connected either in series to the RLC or that resistance may be connected across the capacitor. Here, that load resistance may be connected either in series to the capacitor or that load resistance may be connected across the capacitor like this. Depends on the value of the load resistance. For low and medium resistances, this resistance is connected in series to the capacitor, and for high value of the load resistance, that is connected across the capacitor. Why you connect this high value of the resistance across the capacitor means, if we keep the high value resistance in series to the capacitor, there may be a chance the current flow through the SCR is never reaches the latching current. Never reaches the latching current. So if you keep high value of the resistance, then the current flow through the SCR is very low. That current may be below the latching current. If the SCR's current is below the latching current, you need to provide the continuous gate pulse. Hence why, for low value of the load resistance, the circuit of class A commutation is like this. All are connected in series. And if you go through the high value of the load resistance, that load resistance must be kept across the capacitor, and the combination of inductor and the capacitor are connected in series to the source. That is the circuit configuration of class A commutation. Coming to the operation, so initially we provide the positive terminal of the supply to the anode of the SCR, and the negative terminal of the supply is connected to the cathode of the SCR. Then the SCR comes to the forward biasing mode, and at time t is equal to 0, we provide the gate pulse to the SCR. At time t is equal to 0, we provide the gate pulse to the SCR. Then what happens? The SCR comes to the forward conducting state. So at time t is equal to 0, the SCR comes to the on state, and the source voltage is transmitted to the load, and the current flow through the circuit is given by this VDS plus, thyristor, inductor, capacitor, and the resistive load. So here this is the current flow through the SCR is increases, and if the SCR is in the on state, there is no voltage across the SCR, hence why the voltage across the SCR is 0. The voltage drop across the SCR is 0. And here this is the voltage across the capacitor. At time t is equal to 0, assume this voltage across the capacitor is 0. At time t is equal to 0, once the SCR starts conducting, then the capacitor starts charging like this. Capacitor starts charging. Whenever the voltage across the capacitor reaches the source voltage, like here at this instant, the voltage across the capacitor is equal to the source voltage. Whenever this voltage across the capacitor is equal to the source voltage, then there is no potential difference in the circuit, and the current flow through the SCR is 0. Hence why at this instant the current flow through the SCR is 0, and after this instant the capacitor starts discharging. Then the negative voltage will be available across the SCR. The negative voltage will be available across the SCR, and up to this, here you can assume the current flow through the SCR is 0 and the negative voltage is available across the SCR. Then the SCR is going to be commutated at this instant, hence why after that there is no current flow through the SCR, and the total source voltage is available across the SCR. Up to this, the capacitor starts discharging. The capacitor starts discharging. The capacitor starts discharging, and here whenever this capacitor is completely discharges, again we need to provide the gate pulse to the SCR. Here again we provide the gate pulse to the SCR. Then again at this instant the capacitor starts charging, and you have some current flow through the SCR, and corresponding that there is no voltage drop across the SCR, and the voltage across the SCR is 0. So in this way, depends upon the charging condition of the capacitor, we are going to be commutated the SCR. So simply in class A commutation, whenever that voltage across the capacitor reaches the source voltage, then the current flow through the SCR is 0, and the capacitor's voltage appears as the reverse voltage across the SCR, and the negative voltage will be available. So here we will meet the two conditions which the SCR is said to be in the off state. Once the current flow through the SCR is below the holding current or 0, and second condition, the negative voltage will be available across the SCR to regain its forward blocking capability of the SCR. If you fulfill these two conditions, at this instant you said the SCR will be in the off state. So this type of commutation technique is used in series inverters. This type of class A commutation is used in series inverters. And for reliable operation of this class A commutation, the selection of the commutating elements, inductor and the capacitors, in addition to the load resistance, they must be obtain the underdamped resonant condition. The selection of the commutating elements, inductor and the capacitance, must obtain the underdamped resonant condition corresponding that the class A or load commutation must works reliably. So this commutation technique is used in series inverter applications, that is class A commutation. And coming to this second forced commutation technique, class B or resonant pulse commutation. So here this is a circuit representation of class B or resonant pulse commutation. In class B commutation, the commutating components are connected across the SCR, whereas in class A commutation, the commutating elements are connected in series to the SCR, whereas in class B commutation, the commutating elements L and C are connected across the SCR. So see here, at time here anode is made positive with respect to the cathode, and at time t is equal to 0, we provide the gate voltage across gate and cathode terminals. So at time t is equal to 0, the SCR comes to the on state. Once the SCR comes to the on state, there are two currents should flow through the load terminal. One is the source SCR, RL and the VDC minus. Another one is the source, inductor, capacitor, load resistance and the source. So whenever you provide the gate pulse to the SCR, then two types of the current should flow through the load. One is the current through the SCR and the load. Another one is the capacitor charging current, inductor and the capacitor, like this. So here there are some current should flow through the SCR, and similarly we have load current like this. Whenever the capacitor is fully charges, then the capacitor starts discharging. That discharging current will be oppose the current flow through the SCR. The capacitor discharging current will oppose the current flow through the SCR. So whenever this capacitor discharging current dominates the current flow through the SCR, then the SCR may goes to the off state. See here. So when SCR is triggered, the current flow in two directions. One is through the VDC, SCR, R and VDS minus. Another one is the commutating current through inductor and the capacitor components. And here, once the SCR is turned on, the capacitor starts discharging through the capacitor, inductor, thyristor and the capacitor like this. Capacitor, thyristor, inductor and the capacitor. This is the capacitor's discharging path. So, here that capacitor starts charging up to the value E. When the SCR 2 is triggered, wait a minute, this one. When the capacitor is fully discharges, it starts charging with reverse polarity. Hence, a reverse voltage is applied across the SCR which causes the commutating current IC to oppose the load current. So, when this commutating current IC is higher than the load current, then the SCR is automatically goes to the off state. So, here depends on the charging condition of the SCR, charging condition of the capacitor, the SCR maybe goes on and off. Here simply the SCR is turned on for some time and automatically turned off for some time. So, that continuous process will decide the required frequency depends upon the value of inductor and the capacitor. So, if you provide the gate pulse to the SCR, it comes to the on state and depends upon the charging condition of the capacitor, the SCR is automatically goes to the off state. This class B commutation is also called the self commutation. So, sometime the SCR will be in the on state and some time period the SCR will be in the off state. So, on and off depends upon on and off we are able to control the output voltage. So, this type of commutation techniques is used in chopper circuits. So, here the class B or resonant commutation is used in the chopper circuits. And third one, is the class C or complementary commutation. So, if we go through this circuit diagram, this is a circuit representation of the complementary commutation or class C commutation. In class C commutation, we use some external SCR which is used to commutate the main SCR. Here, this SCR1 is the main SCR and SCR2 is the complemented SCR which is used to turn off the first SCR. And in the circuit diagram, the source and the resistive load and the SCR is the representation of main circuit and resistance, another thyristor, capacitor, this is the representation of commutating circuit. In main circuit, the load resistance is always connected in series to the main SCR. The load resistance is connected in series to the main SCR and the commutating SCR or the additional SCR is connected across the main thyristor. This is the complemented SCR is connected in parallel to the SCR. So, coming to this operation, initially both the thyristors are in the off state. Initially both the thyristors are in the off state. We never provide any gate pulse to the two thyristors and there is no charging to the capacitor, there is no current flow through the capacitor. So, initial voltage across the capacitor is also 0. At time t is equal to 0, we provide the gate pulse to the first thyristor. At time t is equal to 0, we provide the gate pulse to the first thyristor like Ig1. Then what happens? The current flow through the load is like this. The current flow through the circuit is like this. And the capacitor starts charging through these resistance, capacitance, thyristor like this. So, initially both the thyristors are in the off state Hence why there is no current flow through the circuit and the charging voltage across the capacitor is 0. Now we provide the gate pulse to the first thyristor, then the charging current flow through the capacitor is like this. And the source is connected to the load through the thyristor 1. See here, this is the operation. Initially both the SCRs are in the off state, so the capacitor voltage is 0. When SCR1 or main SCR is triggered, then the current starts flowing in two directions. One is VDC plus RL, thyristor, and VDC minus. Another path is VDC, R, capacitor, thyristor, and the VDC minus. So here the capacitor starts charging up to the source voltage. The capacitor starts charging up to the source voltage. Then if you provide the gate pulse to the second SCR at this instant, up to that they have some voltage and there was some current flow through the load. And whenever you provide the control signal to the second thyristor, what happens here? When the SCR2 is triggered, then SCR is turned on and simultaneously a negative voltage is applied across the SCR1 during the discharging condition of the capacitor. So when SCR2 is triggered, the negative polarity is applied across the SCR1. So this reverse voltage across the 1 immediately causes to turn off the SCR1. And similarly, the capacitor starts charging through the reverse polarity to the path VDC, RL, C, like this. Like this. The capacitor starts charging due to the condition of SCR2 is on, then the capacitor's charging path is RL. Now the polarities can be changed, C plus, C minus, SCR2 and the VDC minus. This one. Like this. VDC, RL, C plus C, SCR2. And again, if you provide the control signal to the first SCR and the capacitor starts discharging, and this may cause the reverse polarity across the SCR2, and if you provide the gate pulse to the first thyristor, then SCR2 is going to the off state, and again the circuit like this, and again capacitor starts charging, and again whenever this capacitor is fully charges, if you provide the gate signal to the second thyristor, then this negative voltage across the capacitor may appear as the reverse voltage across the main thyristor, and SCR1 is going to the off state. So in this complementary commutation, if you want to turn off this SCR1, then this capacitor's voltage appears as the reverse voltage across the SCR2. And if you want to turn off this SCR2, this voltage across the capacitor may appear as the reverse voltage across the SCR2, and we provide the control signal to the T1. In this way, periodically by on and off of this T1 and T2, we are going to operate that circuit. This type of application is mainly used in McMurray-Bedford inverters. McMurray-Bedford inverters, we mainly use this class C commutation or complementary commutation. This is very reliable method and it is used even at frequencies below the 1000 Hz. So if you go through the McMurray-Bedford inverters, simply we go through the class C or complementary commutation. And next, coming to the fourth classification of the forced commutation technique, class D or auxiliary commutation. So in this class D or auxiliary commutation, this is the circuit diagram representation. So here, this is the source and SCR1, resistive load. These three elements simply represents the main circuit, and capacitor, SCR2, inductor and the diode simply represents the commutation circuit. Source, SCR1, resistive load simply represents the main circuit, capacitor, SCR2, inductor and the diode simply represents the commutation circuit. So coming to this operation, here the main SCR is going to be commutated by using the auxiliary SCR, hence why this is called auxiliary commutation. And so when the supply voltage E is applied to this circuit, initially both the SCRs are in the off state. So initially both the SCRs are in the off state, and at time t is equal to 0, at this instant we provide the gate pulse to the first thyristor or main thyristor, then the current flow through the circuit is VDC plus, SCR1, load resistance and VDC minus. So at time t is equal to 0, if you provide the control signal to the main SCR, then the current flow through the circuit is VDC plus, SCR1, load and VDC minus. And so VDC plus, and here the capacitor will be charges through the path VDC, C, SCR and the VDC minus. So like this, in this manner. So if you provide the gate pulse to the first thyristor, the load current flows through the circuit in this way, that is VDC plus, SCR1, load, VDC minus. In this way the load current will be flow through the circuit, and the capacitor's charging current IC will be flows through the path VDC plus, capacitor, SCR2 and the load resistance. And here whenever this capacitor's charging current, whenever this charging current is greater than this current flow through the SCR, or the voltage across the capacitor will reaches the VDC, then the capacitor starts discharging. Whenever this capacitor's discharging current greater than the current flow through the main SCR1, then the SCR is going to be off state, and the energy stores in the inductor is now the capacitor discharges path. Here when the SCR2 is triggered, the capacitor starts discharging that C plus, SCR2, SCR1. So when this discharging current is more than the load current, then the SCR1 becomes off state. So here in class D commutation, this main SCR is going to be commutated by using this external circuit, external capacitors and the main SCR, auxiliary SCR2. So this type of commutation technique is called class D commutation or auxiliary commutation. And last one, class E or external pulse commutation, last classification of the forced commutation technique. In this external pulse commutation, we use some pulse generator which is used to provide the voltage across gate and cathode terminals of the SCR to commutate this main SCR. So initially here VDC is plus and VDC minus, and when anode is made positive with respect to the cathode, then SCR is comes to the forward biasing mode. At time t is equal to 0, we provide the gate signal to the first thyristor, then the SCR1 is comes to the on state. So when the SCR is comes to the on state, this is the current flow through the circuit, and see here there was some current flow through the SCR. As long as the SCR will be in the on state, the voltage drop across the SCR is 0. At this T1, I just want to turn off this SCR1 by using some external pulse generator. Will provide the signal to the gate and cathode terminals, corresponding that the voltage available across this pulse transformer appears as the reverse voltage across the thyristor. So this reverse voltage across the thyristor is used to turn off the thyristor 1. So at this instant T1, if you provide the external gate pulse to the SCR, from this instant the SCR goes to the off state, and the total source voltage is available across the SCR as long as you maintain the off state of the SCR. And again at this instant T2, again I provide the gate pulse to the T1, again it comes to the forward conduction state, hence the voltage across the SCR is 0 and there was some current flow through the SCR. If you want to turn off that SCR, we need to provide the negative voltage across gate and cathode terminals by using this external pulse generator, and once the SCR comes to the off state, again if you want to turn on, we provide the gate pulse by periodically by on and off of this SCR, we are able to control the voltage in the circuit. That is a simple class E or external pulse commutation. Protection of the SCR, the next topic. We already said all the power semiconductor devices have low thermal handling capability. That means even for a small period of time, if the voltage across that SCR and current flow through the SCR crossovers its rated values, then those devices may go to the damage. So for safe and reliable operation of that SCR, you must ensure that the current flow through the SCR and voltage across the SCR cannot exceed the rated value. So always the operating values must be below the rated values for safe and reliable operation of that SCR. But depends upon the switching condition of the SCR during the transient state of the SCR, there may be a chance of the current flow through the SCR, or due to some abnormal operating conditions, the voltage across the SCR may exceed its rated value, hence why you need to protect the SCR. So to avoid that undesirable effects on the SCR due to these abnormal operating conditions, the SCRs must be provided with suitable protection circuits. So some of the protection techniques employed for the SCR include over voltage protection, over current protection, dV by dt protection, and di by dt protection. Here we are discussing these over voltage protection, over current, thermal protection, high dV by dt and high di by dt. These are the different types of protection schemes available for satisfactory operation of the SCR. If you go through this over voltage protection, these over voltages are the greatest cause of the failure of the SCR. So these transients over voltages often lead to unscheduled turn on of the SCR. So due to these over voltages, what is the meaning of unscheduled turn on will be discussed in dV by dt protection, and may lead to the permanent destruction of the SCR if the reverse transient voltage is more than the reverse breakover voltage. Here this reverse breakdown voltage or reverse breakover voltage, if the voltage across the SCR is in reverse biasing mode, you must ensure that the voltage across the SCR under reverse biasing mode is below the reverse breakdown voltage. If the voltage across the SCR under reverse biasing mode crossovers the reverse breakdown voltage, then the SCR may goes to the damage. And there are several causes of appearing these over voltages like commutation, chopping, lightning effects, or like in rainy seasons due to these abnormal operating conditions, the transient voltages must be taken place. So depends on the sources. Over voltages are divided into two types, like internal over voltages and external over voltages. The effects of the over voltages can be minimized by using non-linear resistors called voltage clamping devices like metal oxide varistors. you must keep in the circuit. And if you go through the overcurrent protection, this overcurrent protection and mainly occurs due to the different types of faults in the circuit. So due to this overcurrent, the I square R losses will be increased and it produce high heating effect due to these I square R copper losses that exceeds the permissible limit and burn the SCR. So the SCR can be protected from the overcurrents by using either circuit breakers or fast acting current limiting fuses. Very, very important. These fast acting current limiting fuses are used to protect the SCR from overcurrents. Hence why this is called overcurrent protection. Fast acting current limiting fuses. And the circuit breakers are used for protection of the thyristor against continuous overloads or against surge currents of long duration, as the circuit breakers has long tripping time. But fast acting fuses are used for protecting the SCR against the high surge current of very short duration. And next one, high temperature protection. With increase in the temperature of the junction, insulation may get failure. If the junction temperature exceeds certain value, then the insulation failure is taken place between the layers or power semiconductor layers, then the SCR may goes to the damage. So we can achieve this, that temperature protection should be achieved by mounting this thyristor on the heat sinks, which mainly made by high thermal conductivity materials like aluminum or copper. So mainly aluminum is used due to its low cost. There are several types of mounting techniques for SCR such as lead mounting, stud mounting, bolt down mounting, press fit mounting, press pack mounting. Different types of packing techniques are available in the SCR to protect the SCR from this high temperature protection. And next, high di by dt protection. So when a thyristor is turned on by providing the gate between the gate voltage between the gate and cathode terminals, then near the junction J2 we have the gate terminal. So we provide the voltage across gate and cathode terminals. So if the rate of rise of anode current, that is the di by dt, is greater than the velocity or spreading of charge carriers, then the localized hotspots will be generated which produce the local hotspots. Like if you go through the SCR, in the structure of the SCR we have the 4 layers. This is the cathode and this is the anode. This is P, N, P and the N. The outer P layer is considered as anode, then outer N layer is considered as the cathode. Here we have the gate terminal. So whenever you provide the voltage across gate and cathode terminals, then this gate terminal injects the electron hole pairs inside the junction J2. So the rate of rise of current is greater than the spread velocity of the charge carriers, then the local hotspots will be formed at the junction J2. If the local hotspots will be formed, means the junction temperature may be increased. If the junction temperature exceeds certain value, then the SCR may goes to the damage. So to protect this SCR from this di by dt protection, you use inductor in series with the SCR. In series with the SCR, we use an inductor to protect the SCR from this di by dt protection. And last one, dV by dt protection. What is the need of this dV by dt protection means? We already discussed different turn-on methods of the SCR like forward voltage triggering, dV by dt triggering, temperature or thermal triggering, light or radiation triggering and gate triggering method. Out of these 5, the gate triggering method is most economical, efficient and advantage triggering method. But if you go through this dV by dt triggering method, what is the meaning of dV by dt triggering? Even though you provide the low voltage across anode and cathode terminals, if the rate of change of voltage across the SCR is high, then the SCR may goes to the off state. Due to this dV by dt triggering, what happens means the unwanted conduction or unscheduled triggering must be taken place. What is this unwanted triggering means? For simple example, if you go through the choppers, like step down chopper, the output voltage formula for the step down chopper is V0 is equal to alpha into Vs. And here alpha is the duty cycle ratio which varies from 0 to 1. It is the output voltage, it is the source voltage. For example, I have the source voltage 100 volts and I want to collect this output voltage 50 volts. Then you maintain the duty cycle ratio 0.5. You maintain the duty cycle ratio 0.5. If you maintain the duty cycle ratio 0.5, then you are getting the output voltage 50 volts from the input 100 volts. So if alpha is nothing but T on by T, that is, if you consider the total time 10 milliseconds, then the on time must be 5 milliseconds. So for safe and reliable operation of this step down chopper, if you want to collect the 50 volts as the output from the 100 volts input, you need to maintain on time 5 milliseconds and off time 5 milliseconds. So if you maintain like this, then you are collecting the 50 volts as the output voltage, no problem. So initially you maintain on state 5 milliseconds. Okay. Next 5 milliseconds we keep the SCR in the off state. But if there is any disturbance or due to these abnormal operating conditions, if the rate of change of voltage across the SCR is high, then the SCR may comes to the on state. That means before 5 milliseconds, if the SCR comes on at 3 milliseconds, then the output voltage can be changed. How that output voltage will be changed? The unwanted conduction should be taken place. Unwanted means I just want to maintain on state 5 milliseconds and off state 5 milliseconds. But if the dV by dt rating exceeds its rated value, then the SCR comes to the on state. That is nothing but unwanted conduction should be taken place if there is rate of change of voltage across the SCR is greater than its dV by dt rating. That dV by dt rating is given by the manufacturer. It varies. That value varies from 20 volts per microsecond to 200 volts per microsecond. Depends upon the rating. 20 volts, for example, and not 200 volts. For higher rating of the SCRs, the 200 volts may be varies. How much dV by dt rating is available for particular rating of the SCR, that should be given by the manufacturer. So here this dV by dt protection is used to avoid the unwanted conduction taken by the SCR due to this dV by dt value. So how you avoid that dV by dt protection means the circuit which is used to avoid that dV by dt protection is simply called the Snubber circuit. The Snubber circuit consisting capacitor and the resistor. Here this capacitor is called Snubber circuit capacitance and this resistance is the Snubber circuit resistor. Snubber circuit is used to protect the SCR from dV by dt rating. Hence why it is called dV by dt protection circuit. And this inductor is used to limit the di by dt current. So to protect the SCR from this di by dt rating, we keep an inductor in series to the SCR and this Snubber circuit which consisting capacitors and the resistance are kept across the SCR. Actually this capacitor is sufficient to protect the SCR from the dV by dt rating. What is the need of the resistance here? If this capacitance is in the, if this SCR is in the off state, then the capacitor is charged up to the rated voltage. Once the SCR comes to the on state, the current flow through the SCR is the load current. Another current is capacitor discharging current. So there may be a chance the current flow through the SCR exceeds its rated value. Hence why, to limit that current flow through the SCR below the rated current, we keep resistance in series to the capacitor. Here what is the function of the resistance means? It opposes the discharging current flow through the SCR. Hence why this is current limiting resistor. This Snubber circuit resistor is called the current limiting resistor. So Snubber circuit is always connected across the SCR. This is the combination of the Snubber circuit. It is always connected across the SCR, and the Snubber circuit consisting resistance and the capacitance which are connected in series to the each other. So coming to this operation, working of the Snubber circuit. So as long as here initially the switch will be in the open position, and if the switch is closed, here anode is made positive with respect to the cathode, then the SCR is in forward biasing mode, and the capacitor starts charging slowly. If the what is the function of the capacitor? It does not allow the sudden change of voltage. After just closing the switch, the voltage across the SCR is 0, and depends upon the charging condition of the capacitor, the voltage across the SCR is gradually increases. So when the switch is closed, the voltage equation is given by here Vs is equals to I into R plus L into di by dt, plus L into di by dt. And here the values of the inductors and the resistance and the capacitance for reliable operation of that SCR, the value of the inductor is given by L is equals to Vs into di by dt maximum, and the value of the resistance is given by Rs is equals to L by Vs into dV by dt maximum, and the value of the capacitance is find out by using this relation. Rs is equals to 2 zeta into root of L by Cs. Rs is equals to 2 zeta into root of L by Cs. These are the fundamental formulas which you remember, and these formulas are very useful in solving the problems on Snubber circuit parameters. The Snubber circuit parameters, L is equals to Vs into Vs divided by di by dt maximum, and the value of the resistor Rs is equals to L by Vs into dV by dt maximum, and the value of the capacitor should be find out by using the relation Rs is equals to 2 zeta into root of L by Cs. This is a simple Snubber circuit parameter. So in this class we just discussed the different turn off methods of the SCR and protection of the SCR. Thank you.